To meet everybody. So I'm Elizabeth Meckes, and I'm doing these talks on concentration phenomena in the compact classical groups. So let me just say before I start talking about all of those words and what they mean, that I'm really excited to be here, and I was completely thrilled to be asked to come. I've never been IAS before, and I've certainly never gotten a chance to be involved in a program like this, and I think it's really exciting. So I also kind of wish I'd known about it when I was younger, although I was such a snob that I probably would have just not come, which would have been my loss because it seems like it's a really great program. So it's really exciting to be here. Also, I was thinking about what I wanted to talk about, and I was trying to think where I had learned this stuff that I wanted to tell you about, and I actually couldn't figure that out. So I asked some other people where I learned this stuff. Conveniently, my PhD advisor is visiting the same place I'm visiting right now, so I asked him, and he didn't know either. Which is incidentally Toulouse. I should probably tell you that. So I am an associate professor of mathematics at Case Western Reserve University, but right now I'm on sabbatical. So I am living in Toulouse, which is in the south of France, which is definitely one of the perks of academia, is you get to go exciting places like that. So anyway, right now I'm in Toulouse, which is a great environment, and incidentally, my PhD advisor, Percy Diaconis, is also there, so we've had lots of nice chats this year, but he was not able to help me as to how I learned stuff about the compact classical matrix groups. So I started writing up some notes, thinking, well, I'll just make up some lecture notes that I can distribute to everybody, and they kind of got a little out of hand. So they're about 50 pages at this point, so I definitely can't talk about all of it. I'll email it to all of you so that you have just kind of a record of what we're saying. So this is a really wide range of backgrounds, and I know that, so I'm going to try to just kind of give you a flavor of things. So for some of you, probably everything I say is going to be completely clear and easy. And others of you, it's not intended to be followable, every little detail. Just try to get kind of the big picture. And I did write down a lot more details in the notes, so I'll email you those if you're interested in looking at the details. And then there are the review sessions as well. So, OK. So we're going to talk about Harmeasure on the compact classical matrix groups. So what are those? What is an orthogonal unitary symplectic matrix? I mean, I want to tell you what's a random matrix from one of these groups. But before we do that, let me just tell you what the matrices are themselves, partly to make sure we're all on the same page, but partly because I find that, a lot of times we sort of introduce the formal kind of algebraic definitions, but to me these are very geometric objects, and I want to think about them in terms of the geometry. So we have the orthogonal group, which I guess I'll try to write this way. That's supposed to be an O, not a Q, sorry. So this is the orthogonal group. Okay, so this is n by n matrices. Let's call them U. So kind of for historical reasons, I'll call them all U, because all of these are unitary groups in some sense, although only the middle one I actually call that. So we have the orthogonal group, which is n by n matrices U over R, such that the following holds. So U transpose is U transpose U is the identity. So the transpose is the inverse. OK, fine. I mean, that's a perfectly legitimate definition. OK. That's a matrix. What does that mean? To me, so this is the way I like to think about it, is that the columns, or the rows, so note that this is invariant under taking transpose. Okay, so I can think about either the matrix or its transpose, which I'll do all the time. Okay, so if it's more convenient to talk about columns, more convenient to talk about rows, I'll just do that. Okay, because everything here is invariant under transpose in the matrix. Okay, the columns of U form an orthonormal basis of Rn. Okay? And that's how I really think about these objects. That's not the only way to think about them. So this is one way, is just to think about it in terms of, okay, this is a perfectly legitimate algebraic condition on the entries. Fine. Okay? You can stop there. This is another way. So I think of this as just encoding all of the possible orthonormal bases of Rn. Okay, I can make the columns of a matrix. I can take the standard basis if I want, and I could make the columns of a matrix, and if I put them in order, I'd have the identity matrix, which definitely satisfies this. Okay? Or if I put them in the wrong order, Okay, then I would have a permutation matrix, which also satisfies this. Or I could have some other orthonormal basis, and I could make those the columns of my matrix. Then I'd have some other orthogonal matrix. Okay, so this is how I usually think about these things. It's not hard to check that this is equivalent to this, right? All you have to do is write down what's the ijth entry of this. Okay, the ijth entry of a matrix product, right? You take the row from one, the column from the other, and you're taking the dot product, right? And this guy's being transposed. So here I can think of the ijth entry as the dot product of the ith and jth rows of U. Here I can think of the ijth entry as the dot product of the ith and jth columns. Okay, so to say that that matrix is the identity is exactly to say that the dot product is delta ij. Okay, so the columns are an orthonormal basis. Great, that's getting into a more geometric setting. Also, you might like to think that these are the matrices, so these are exactly the matrices which act as isometries on Rn. So we have uv dot uw is equal to v dot w for all v and w in Rn. And this is also a way to think about orthogonal matrices, is they are the matrices that act as isometries on Rn. Okay, so that makes me happier because now this is sounding much more geometric. And it sounds much more like something I can think about. This is just kind of like, okay, I can write down a formula, but I don't know how to think about it. So this is the orthogonal group. The unitary group I'll probably forget to write the Blackboard bolds, but you know. Okay, so U of n is the complex version. Okay, so sometimes people call this the real unitary group. It's analogous to this, but over reals, these are over complex. So these are n by n complex matrices such that UU star is U star U is the identity, and this is the U star is the conjugate transpose. Okay, so this makes sense. I'm living over the complex numbers. I don't just take the transpose, I take the conjugate transpose, or if you like, I take the adjoint of this guy as a linear map on Cn. Okay, so that's the unitary group, and similarly, the columns, or the rows, are an orthonormal basis of Cn, okay, with a complex inner product where I dot two vectors by multiplying, the ith component of one with the complex conjugate of the ith component of the other, and then adding them up. Okay, so this is exactly analogous to this, and then we have this kind of thing as well. Okay, so good. So that's the unitary group, and then finally we have the symplectic group. So in this part of the world where people who are working on random matrices from these groups, we kind of like, for form's sake, we talk about the symplectic group. And there are people who care a lot about the symplectic group. It's just that in this area, people usually just say, well, yeah, and then there's the symplectic group, and they kind of ignore it. So I don't know why. So I can define it in a couple of different ways. One way is to say, so these are 2n by 2n matrices over C, such that the following weird condition holds. I have to call it U again. So I get uj u star is u star j, u is j, where j is this matrix. So it's 2n by 2n, and it's blocky. Okay, so here's a 0 block, and then here's the n by n identity. Here's a 0 block, and here's a minus the identity. Okay, and if this condition makes you happy, that's great. And if it doesn't, I'm not really going to talk about it that much, so don't worry about it. So actually, this object is more natural than this makes it look. Or at least, this does not look natural to me, probably due to my upbringing. But so to some people that looks very natural. To me, it makes this whole thing sound much more natural if I say the words, which turn out to be true, that what this is it's the octonian unitary group. So if you take an n by n matrix, and it's a matrix over the, quaternionic unitary group. If you take an n by n matrix with quaternionic entries, okay, this is the unitary group. That is, it satisfies this condition here, u star equals u star u equals the identity, where that time star has to be interpreted as the quaternionic complex conjugate, so you change the signs of the ijk's and you leave the real part fixed. And then there's this whole business that you can represent quaternions as 2 by 2 matrices over C, and if you take a look at the notes I wrote up, you'll see a little footnote saying you should be able to grind it out and see that this condition is the same as this, but I started to and I got bored and I stopped. Okay, so apparently they're the same. Many people have told me so. Like I said, we don't really care about this one that much, but we just kind of do it for form's sake because it's in there. And there are some people who do serious stuff with that, but I'm not one of them. So, sorry. Okay, so anyway, these are the matrix groups that I want to be talking about. And hopefully, at least not, maybe not from the initial condition, but hopefully by these kinds of statements, you're willing to spot me for the moment that these are sort of natural and interesting geometric objects. Okay? So I'll talk a little bit more later about why we would care about trying to find a random one. But for now, let me just say a couple more things about geometrically, just a couple of tiny things. So one, which is not hard to see at all, is that if u is in, I'm going to switch notation. Sorry about this. It's just easier to do it this way because it's easier to write a script u than a Blackboard bold u. So if u is in u of n, then I should have done it the other order. Then the determinant of u is a modulus 1 complex number. If u is orthogonal, then, well, same statement, determinant of u is a modulus 1 real number, so it's plus or minus 1. Okay? So, and I'm going to stop talking about the symplectic group now. So because of this, something that we do sometimes is we talk about the special versions of the orthogonal and unitary groups. So we have SON. This is the special orthogonal group. Okay, special because these are the matrices with determinant 1. So this is u in O of n such that the determinant of u is equal to 1. So in this case, it's half the group. Okay, half the group has determinant 1, half of it has determinant minus 1. Okay, sometimes we want to work with those two, so I may as well go introduce notation now. So SO minus of n, this one doesn't get talked about as much, but it's a useful technical tool. It doesn't really have a name. Sometimes people just call it the negative coset. So this is u in On such that the determinant of u is equal to minus 1. Okay? And so the orthogonal group is different from, for example, the unitary group in that it's disconnected. It consists of these two separate components, the special orthogonal group, which is a group by itself, and the negative coset, which is not a group. Okay, this isn't closed under multiplication because if you take two of them and you multiply it together, you get determinant 1. Okay? But it's a coset of this group inside of that group. Okay? So good. So that's the special orthogonal group and its negative coset. And then we have the special unitary group, which is the unitary matrices with determinant equal to 1. And so this is a very different situation because in the unitary group, you can have any unit modulus complex number be the determinant. So you have the whole circle of possibilities for the determinant. And here we're picking out just this one. So we don't have this disconnected thing happening here. This group is connected, but this one's not. OK. I should have said at the beginning that, of course, you are definitely encouraged to stop me and interrupt me, and definitely also encouraged to stop me and slow me down if need be. I know I talk really fast, but I've kind of given up on trying to talk slower, so I just hope that if I encourage people to interrupt me a lot, that'll kind of counteract it. So please interrupt me if I say anything weird or just confusing. So OK with the definitions, these are the kinds of matrices I want to think about. Good. OK, what else do I want to say about them? There are isometries. Good. OK, so we're going to talk a lot about these groups. So these are one of the things that I love about working on random matrices from these groups is that there are so many different areas of mathematics that are really important And if you want to really understand matrices from these groups and random matrices from these groups, it means that you have to know about representation theory, and you have to know about Riemannian geometry, and you have to know about Euclidean geometry, and you have to know about all kinds of things. So it's really beautiful the way all of these ideas come together. And so I don't want to talk too much yet. We'll get into some of that more in a couple of days. But for now, let me just say that all of these are compact Lie groups. So that's fine. They're compact Lie groups. I do want to talk a little bit about their metric structure. Okay, so we can think of, let's for simplicity just talk about the orthogonal group, because I'm a simple-minded person and real numbers are easier for me than complex numbers. So let's think about the orthogonal group. So the orthogonal group sits inside Rn squared, right? I mean, I can think of that because it's a box of numbers. It's n squared numbers. These are n by n matrices. So I can think of them as sitting inside of Euclidean space. Okay? It's not especially natural for me to think of a box of numbers as a little arrow, but I mean, it is a set of n squared numbers, so I can think of it inside of Euclidean space. Okay? Which is good because I know a lot about the geometry of Euclidean space, so hopefully it can tell me about the geometry of this object. Okay? So we can do a little bit better than just kind of, it feels a little unnatural to say, oh, well, I can make it into a list of n squared numbers by, some ordering. I mean, yes, I can. But usually we don't. What we do is say, if I made this into a vector, if I made an n by n matrix into a vector, and I took the dot product of two of them, then I would still be doing what we know you do when you take the dot product. I'd be multiplying corresponding entries and adding them up. Okay? So the dot product of, let's say, u and v, no matter how I sort of try to realize this, it's going to be the sum over all the entries, so I and j go from 1 to n, of u, I, j, v, I, j. Okay, I take corresponding entries and I multiply them together and I add them all up. Okay, so this is the trace of uv transpose. It's just a formula. Okay? So what we do is, instead of trying to kind of think of this as a long pointy arrow, instead we just say, well, O of n sits inside of Euclidean matrix space. So I'll call it Mn of R. This is the space of n by n matrices over R. And this space is a Euclidean space in that it is endowed with an inner product, and the inner product is this one. Okay? So I can just think of everything in matrixy language, and that's really what I want to be able to do. So I have UV, so this is sometimes called the Hilbert-Schmidt. Hilbert-Schmidt inner product, and it's just exactly what I wrote there. So it's the trace of UV transpose. So there's no reason to write it again, but there it is. Okay? So this is, when I talk about this group sitting inside of Euclidean space, I don't really mean Rn squared. I mean Mn of R, the space of n by n matrices over R, endowed with this inner product. Okay? So I can think of this then as a submanifold of this particular Euclidean space. Okay? And because it's a submanifold of this Euclidean space, then I can think about its manifold structure that it inherits from the Euclidean space that it sits inside. So there are actually two ways to do that. So well, let me say there are two ways to do that. So two metrics on ON or UN or whatever. So one of them is what I can get by just measuring distances inside of Euclidean space. Okay? So let me draw a picture. I should really be talking about the unitary group just because, well, it doesn't matter. So let me just draw a picture, and this is a schematic picture, or if you like, it's a picture of U of 1. Inside of Euclidean space, I have this submanifold, okay, which I will suggestively draw like that. Okay? Now, if I have 2 points, I have 2 ways to measure distances between them. One way is I can measure the straight line distance, because the whole thing is sitting inside of Euclidean space. Okay, so I can perfectly well just see how long this line is. Okay, so that's the Hilbert-Schmidt distance. Okay, so one way is I can measure the Hilbert-Schmidt distance between, say, A and B. They sit inside of Euclidean space. How do you measure distance? You look at the norm, okay, of the difference. What's the norm? Okay, it's the dot product of the thing with itself and then square root. So this is the square root of the trace of A minus B times A minus B transpose. Good. So that's one option. Okay. Another option is the so-called geodesic distance. Okay, and in my picture, you know what it is. It's arc length, right? Since I'm sitting inside of Euclidean space, that's one option is I can say I have to look at paths from one point to another that lie within the submanifold I'm working on. Okay, so I have to look at a path from A to B that lies inside of the orthogonal group, and I have to measure its length as a curve that sits inside of Euclidean space. So either way, I'm using the Euclidean structure, but I'm using it differently. Okay? Just like in the circle, there are two ways to measure the distance between these 2 points, either the straight line or the curved path. Okay? Is there a question? Please seriously stop me if there's a question. No? Okay. So I sort of snuck in there that this is a picture of U of 1, right? So U of 1 is 1 by 1 matrices over C. Okay, so numbers, complex numbers. And they are supposed to satisfy the condition there, UU star equals the identity. Okay, if U is a 1 by 1 matrix, that just means UU bar equals the identity, which means that the complex number has modulus 1. Okay, so U of 1 is the circle. Okay. And so what about O of 1? Yeah, say it out loud. It's 2 points. Which 2 points? Plus and minus 1. Yeah, be brave. Come on. Yeah, that's why we're all heroes, because we're going to be like unafraid to shout things out, and I'll make lots of mistakes just to make everybody more comfortable. It's tactical. Okay. So yeah, O of 1 is 2 points. It's plus 1 and minus 1, so it's disconnected. We already talked about that. And U of 1 is the circle. Okay. So, okay, good. So we have this. So I'll just call it the geodesic distance. Okay, so to compute it, I mean, it's potentially a little bit complicated, right? Because what you have to do to compute it is you're computing the length of an arc. So you have to, in principle, I mean, of course, we can do better than this, but in principle, what you have to do is look at all curves within, in this case, O of n, that go from A to B. Okay? And you can measure their arc length as arcs living inside of Euclidean space. You know how to do that. You learned how to do that in calculus. I mean, you have to take tangent vectors, stuff like that, and do integrals. Okay? So we can do that. And here, it's much easier to think about, because here it's just arc length. Okay? So in this picture, we've got this versus that. So it's not really that important which one you work with, as you might start to guess from that picture. They turn out to be about the same. So on the unitary group, for example, so I have the geodesic distance and the Hilbert-Schmidt distance. So which one's bigger? Yeah, the geodesic distance is bigger, right? Why does it have to be bigger? Sorry?
Oh, because you're taking between them, so any path in the Hilbert-Schmidt is also a path in the geodesic.
Other way, but yeah.
Oh, yeah.
Yeah.
Well,
But yeah, that's exactly right. That's exactly the right issue, right? I mean, either way, we're computing a distance, and we can think of it as the inf over path lengths. Okay? And in the geodesic distance, we're requiring the paths to lie within the submanifold. In the Hilbert-Schmidt distance, we're not. Okay? They're allowed to be anywhere in the ambient space. So for sure, we have that the geodesic distance between A and B is bigger than the Hilbert-Schmidt distance between A and B. And I actually make sure I get the constants right. And the Hilbert-Schmidt distance, pi over 2. I'll put it over here because I have space. Okay, so that's the string of inequalities you have. So they're really basically the same. So this, you might have kind of guessed this from the picture, because this is easy to see if n is equal to 1. Okay, so if n is equal to 1, what you're doing is comparing straight line distance versus arc length distance. Yeah?
is it exactly Euclidean distance with Rn square?
Yeah.
That's what it's exactly.
Yes. Yeah, that's what it is. Just for historical reasons, we call it Hilbert-Schmidt to sort of remind ourselves that we're working in matrixy space. But yeah, it's Euclidean distance. That's right. So what I was saying is that you can guess from the picture that something like this might hold. However, you might have guessed that the constant here depends on the dimension, and it doesn't. Okay? So that's an important point. Because it means that when we're working with these two notions of distance, it really doesn't matter much which notion of distance we're using, even if we're trying to think of really high-dimensional spaces, which we're definitely going to be doing. Okay, so good. So there's an exercise that you guys can talk about in the review session this afternoon about proving those inequalities. So there's steps. Okay, good. So I think that's almost everything. Yeah, that's pretty much what I wanted to say about the matrices themselves. Yeah, let's skip that. So, okay, this is random matrix program, so let's get some randomness involved. So matrices so far, we have these nice geometric objects. So various people have made the point, especially in recent years, that anything worth thinking about is worth thinking about randomly. We're thinking about a random version. And actually, I really believe that. And one of the reasons I believe that is because, and this idea certainly isn't original to me, one of the ways that it's nice to try to understand a big, complicated object, like one of these groups, is to think about what does a typical element of it look like? You know, what can I say? I mean, I can make some statements that are true for all orthogonal matrices, all unitary matrices, and that helps me get a handle on what these objects are. Like I said in the beginning, you know, I wrote down this algebraic condition. Well, that doesn't do much for me, but when I start writing down conditions, oh, this encodes orthonormal bases, then I feel a little bit more better, because, more better, oh my God. So I feel a little better at that point because I feel like I know a little bit more what it means, but you know, there's a limit to how much I'm going to be able to say that's true about all orthogonal matrices. On the other hand, if I can put a probability measure that's natural, and okay, that's philosophy at that point, but if I can put a probability measure that I believe is natural on the space, and then I can start answering questions about what a random matrix distributed according to that measure is like, that at least makes me feel, I'm a probabilist, so I can't help it, but that makes me feel like I understand a little bit better what these objects are like. If I can say, well, pick one. What's it going to do? Okay? So that's kind of the philosophy. There are many other reasons to care, formal reasons to care about what's a random matrix from these groups. But that's kind of, it's the reason that I think even if you don't care about the other motivations, you should care just because you want to know, you know, what are they usually like? Okay? So what are they usually like? Well, what should it mean to take a random element of this group? So this is really different from what Jana was talking about this morning and what you talked about last week, because then it's sort of a little bit, you know, you were able to say, okay, I'm going to take this empty box and I'm going to start filling it with random variables. Okay? So just, you know, put in, if you want to make a Wigner matrix, then you just, you know, fill in the top triangle with IID random variables, and then you make it Hermitian, and then you're happy. Okay, so that's pretty natural. If somebody says, how do you make a random matrix? Well, I make a matrix and I make the entries random. That's reasonable, okay? But that doesn't work as well here, okay? And the reason it doesn't work as well here is because we want the matrices to lie in these groups, okay? And the condition for lying in this group, it's a geometric condition, it's a global condition. It's not something that is so naturally expressed in terms of the entries. And in fact, that was my original problem with the first definition I gave you. It's just a formula in terms of the entries, but it doesn't give me geometric insight as to what these objects are. Okay? So what I want to be able to do is say, what should it mean to pick something at random? Okay? By which I mean in a natural way from these groups. So you know the answer for U of 1. How do I pick a point at random in U of 1? What does that mean? Sorry? Choose an angle at random. What does that mean? That's exactly right, but can you elaborate?
Some distribution on from 0 to 2 pi.
Okay, I need a distribution on 0 to 2 pi. Not just some distribution though, right? Which one?
You can take uniform.
I can take something else. Yeah. Should I take uniform?
So it depends. What do you want? Do you want uniform distribution in the end?
What does uniform mean? Sorry? No, say that again.
No, everything has equal chance.
Okay, thank you for saying that, because that's exactly the kind of statement that I wanted to hear. So yes, we can put a distribution on angles. So we know what that means. We put a probability distribution on the interval from 0 to 2 pi, and then we just wrap that around, and that gives us a distribution on the circle. Okay, so then the question is, which distribution? How do I know which one I should take? Okay, I mean, probably most of you kind of believe that there really is a most natural distribution on the interval. But then the question is why? I mean, how do we know which is the right distribution? Okay, it's supposed to make every outcome equally likely. Well, that's garbage. I mean, this is an uncountable space. You can't do that. But still, I mean, morally, that's what it's doing. Okay? And how do we say it's making every point equally likely? What should that mean? Okay? Because this is a continuous space, so we can't actually talk about the likelihood of individual points. We can talk about the likelihood of individual tiny intervals. Okay, that makes sense. So if it's supposed to make the outcome equally likely to be in each of these individual tiny intervals, what's that really saying? It's saying that the measure that I want to put on the circle should be translation invariant. Okay? Where by translating, I mean rotating. I mean translating in the group. Okay? Because if it's rotation invariant, then the measure only cares about how long the arc is. It doesn't care about where it is. And then if you start making those really, really tiny, that gets exactly at the idea that each point is equally likely, right? Each tiny little interval is equally likely. Okay? So that's what we want. So from here, we want, so uniform on the circle means translation invariant. And I mean, formally, that really is true, right? I mean, uniform on the circle is uniform on the interval from 0 to 2 pi, and Lebesgue measure is characterized by being translation invariant. Okay, so that's really what we want, is we want something that's translation invariant. Okay, so we're working on groups. So we want the same thing here. We want a probability distribution on these groups, so ON, UN, blah, blah, blah. Actually, I gave a talk last summer in which I gave an introduction to these groups, and I characterized, I talked about the unitary group first, and then I called the orthogonal group the unitary group's kid sister, and the symplectic group was the weird uncle that nobody talks about, because that's really kind of, we just never talk about the symplectic group. So anyway, ON and UN. We want a probability distribution on here, which is translation invariant. Okay, and what should that mean at this point? That is, if U is random, and let me just say GN. Okay, GN is one of ON or UN or whatever, and M is fixed in GN. Then what do I want? I want the distribution of M times U to be the same as the distribution of U, and in the other order too. So, okay? So that's exactly analogous to over here when I said that I wanted whatever distribution I put on the circle to be invariant under rotations of the circle. Okay? That's how we should think over here, is I'm transforming the group. It's acting on itself by multiplication either on the left or the right, and I want the measure to be invariant under that. This distribution is the same as that. Or if you like, I have a measure that if I measure a subset, okay, so if you want to think of it this way, if I have A sitting inside of GN, I can define MA to be M times U for U and A. And then I want the probability of the set A to be the same as the probability of the set MA. Okay? I want to be able to take my subset of the orthogonal group, move it, okay, translate it by this fixed matrix, and have that not change the measure. Okay? So that's what we want. That's what it should mean to take a, if you like, you can insert the word uniform. That's what it should mean to take a uniform random matrix from one of these groups. It should be that there should be a measure which is invariant under this. Okay? And the good news is that there was this very clever guy who figured out that there is one, and there's only one. So his name was Haar. So we have a theorem, which is due to Haar, which is there is one and only one translation invariant probability measure on a compact Lie group. Okay, so that's horribly phrased, and I hope nobody's going to give me a really hard time about the order I wrote things in. Yeah.
Translation theory or just like left translation theory?
Okay, so yeah, so Haar proved more than this. Here I'm only talking about compact Lie groups. So he proved more, and sometimes you have to worry because being invariant under left translation is not the same, potentially, as being invariant under right translation. For a compact Lie group, they're equivalent. Okay, so I'm not venturing into the Lie theory world of, so apparently Haar announced at some point that he was going to do this, that we had these examples on compact Lie groups where we knew that there was this one unique translation invariant measure, and that he was going to prove that was the case on some like huge class of groups, and apparently people thought he was crazy. But he did it, so good for him, and that's very nice. So we have this theorem, which I'm not going to say anything about at all, about where it comes from, but we have this theorem that says that there is a unique translation invariant probability measure on these groups that I'm interested in, and that's what I'm going to mean by saying a random unitary matrix, a random orthogonal matrix. I mean one that's distributed, so we say Haar distributed, okay? Or sometimes we say uniform. Okay, so any questions up until this point? Or am I talking too fast and you want me to say the last 10 minutes again? Or?
Yeah, so what are the properties of compact Lie groups that these groups have? Like,
They are compact Lie groups.
yeah.
I mean, I'm sorry, I don't really understand the question.
Yeah, so my question is, what is a compact Lie group?
Oh, thank you. I should have said that. So I'll talk more about that. So I was kind of trying to sweep that under the rug today because we'll talk about it more in a couple days. So it's a group. Okay, it's a group with matrix multiplication. Okay, so these objects are closed. I can multiply two matrices together and stay within the group. Satisfies group axioms. It's a manifold. Okay, so it's a Riemannian manifold, in fact. Okay, so and as a manifold, it's compact. That's it. Thanks for pointing that out. Yeah, if I use terminology that's not familiar, please ask me, because otherwise I'll just merrily go along talking about all kinds of random weird things. And so let me know.
I just want to say something. I mean, your symplectic group is not compact, right?
No. Yeah, it's the weird uncle, right? I mean,
Okay, that's fine.
yeah. No.
We have somebody here who knows about this. Are you going to talk about this symplectic group?
No, yeah. I mean, honestly, like for form's sake, we kind of prove theorems sometimes, but yeah, I don't want to talk about it. Okay. Yeah. Or no, wait, isn't it? Isn't it? Wait a minute. No. Isn't it compact? It's compact. Yeah. No, I don't know why no, it's compact. It's the... Yeah, I mean, we should be able to see that it's compact because it's just the unitary group for the quaternions. So, yeah, I think it's compact.
Well, I'm used to a real symplectic.
Right. I think that's not the same thing. I'm really not that familiar with the terminology in that corner of the world. So this may not be, I don't think it's the same as that. But yeah, this one's compact. And it has a Haar measure on it. So, and a Haar probability measure, so good. Good, okay, so it is compact. All right, so good. Well, I've told you what random, orthogonal, and unitary, and sort of symplectic matrices are. So we're done, right? So somebody should be yelling at me at this point and saying, well, you haven't actually told us what they are, right? I mean, I've told you that there exists a notion. I've said that apparently this black box tells us, this black box named Haar, tells us that there is one and only one translation invariant probability measure on these spaces. So, I mean, great, but that doesn't really do you any good if you want, I mean, I said that the philosophy here was we want to understand these groups by knowing what a typical element is like, and it's pretty hopeless if I have this, like, abstract existence theorem, okay? So what I want to do for the rest of today is just give you a few different ways to actually build a random matrix from one of these groups. So good. Okay, so how do you do it? So I'll describe 3 different constructions, and all of them turn out to be Haar measure, and all of them look very different. So I was going to start with the most abstract, but I think that's kind of not a great idea. So I think instead I'll start with my favorite. So here's my favorite. It's very hands-on if you're a mathematician, and you don't actually really build things. You just talk about like how you could in principle. And then later I'll talk about one that you can actually do on a computer. So here's the first construction. All right, I said that the columns of U are supposed to form an orthonormal basis of Rn. I'm just going to talk about the orthogonal group just for simplicity, but everything that I say it works in the unitary group too. You just have to put bars places. Okay, so the columns of U are supposed to form an orthonormal basis. So I'm supposed to construct a matrix whose columns are orthonormal in Rn. All right, well, so I'm going to do it one at a time. Okay, I'm going to start by pick U1 to be uniform on the sphere living inside of Rn. Okay, so that you're supposed to believe that I already know how to do. And that, okay, it's the sphere, so you have surface area measure. Okay, if you like, you can think about it, constructing it as thickening up Lebesgue measure and then taking a limit. There are lots of ways to think about it, but okay, I have surface area measure. It's just arc length measure, but the analog in higher dimensions. So I pick U to be uniform in Sn minus 1. It's supposed to be random, so this seems pretty natural. So this is going to be my first column. Okay. So now I have to pick a second column. All right, and I know that it's supposed to be orthogonal. So it's a unit vector. It's supposed to be orthogonal to this guy. Okay? So I'm going to pick it to be sort of as uniform as possible, given that restriction. It has to be, so this guy, we pick U2 uniformly from the orthogonal complement of U1 in Sn minus 1. So what does this notation mean? So this is all of the unit vectors in Rn. This is all of the vectors in Rn which are perpendicular to U1. Okay? So this here is a sphere of one smaller dimension. Okay? So if you think about the picture, so imagine first that I am starting off and n is equal to 3, okay, and I'm living in R3. Okay? So I've got 3-dimensional space, I've got the sphere. Okay, so the first vector I pick is just a random point on the sphere, so it's rotational invariant, I've got a point. Okay? Now I think about what's perpendicular to that point, so I get a plane. I'm sorry, I'm terrible at drawing 3-dimensional pictures. That's why I do high-dimensional geometry. You just give up on the pictures. So I've got this point, got a plane, okay, it's perpendicular to it, cuts through the sphere, gives me a circle, right? The circle is in a kind of random direction, right? Because I chose the normal randomly. So I have a circle in a random direction, but it's okay, it's still a circle. So I still know how to pick a uniform point on that circle. Okay, that's U2. All right, now what? How do I fill in? So in the 3 by 3 case, I'm building a 3 by 3 matrix. The first column is a random point on the sphere. Okay, that's fixed. I've got a plane, cuts through the sphere, gives me a circle. I pick a uniform random point on there. Okay? How do I pick the last one? How do I pick the last column? Which is what? If I have U1 and U2, and you're right, exactly. I have to take something in the orthogonal complement of the span of U1 and U2, and it also has to lie on the circle, on the sphere, the original sphere. So, what are my choices? Sorry? I have one little bit of a choice. Yeah, direction, exactly. I have a choice. I basically have a sign. That's the only choice I have left. Because at that point, I've got a line, and it's crossing through the sphere, and so it hits it at 2 antipodal points, and I have to pick one. Okay, so for the last column, there's not much choice, but there is a little bit of choice. Okay? If I were constructing uniform measure on the special orthogonal group, I would have no choice, because then that would determine which of those signs I needed to take. And if I wanted to construct something uniform on the negative coset, also I would have no choice, because I'd have to take the other one. Okay? But if I want it uniform in the whole group, then at that point, that last one, I only have 2 choices left. So that's how you continue, and okay, you do the same thing in higher dimensions, you just have to do it more times, right? So here, we pick uniformly from here. This is the same thing as Sn minus 2. It's a sphere of 1 dimension lower. We have surface area measure. We can choose something according to the surface area measure there. And then we continue. So U3, I do the same way. I pick something that's orthogonal to both of these, lies on the sphere. Okay? So I've got a sphere in 1 dimension down, and I keep going until I get all the way to the end. And the last one, I only have 2 choices. I have 2 antipodal points left to choose from. And so I just choose each of them with equal probability. Okay? That's my construction. So definitely, I've built an orthogonal matrix. Okay? I built it to be orthogonal. This is a unit vector. This is a unit vector that's perpendicular to this. This is a unit vector that's perpendicular to each of these, and so on. It's an orthonormal basis for sure. Okay? The question is, do I have Haar measure? Have I constructed Haar measure? Okay? And it's pretty natural to think that I should have, because after all, I mean, I did things in this sort of very invariant way. I did things as symmetrically as possible, given the restriction that I wanted to come up with an orthogonal matrix. So what do you do when you have a theorem that tells you that there's a unique thing with a certain property? If you want to check that you've built it, you check that the thing that you've built has that property, and then you invoke the black box. Okay? You say thank you, Haar, and you're done. Okay? So what we have to do is we have to take M, and we have to multiply this matrix by M, and we have to see that the distribution is the same after. It's not the same matrix, okay? We've shifted it, okay? But we need to see that its distribution is the same. Well, okay, if I multiply a matrix that's written this way with columns by a fixed matrix on the left, that just multiplies the columns by the matrix, okay? So if you're not used to this kind of manipulation, you can work it out in the margin of your notes if you feel like it. So, okay, so this is the thing, and I want to know, is this equal, okay, wow, too many decorations. So I need it to be equal in distribution, question mark, we hope, to okay, is the distribution the same? Okay, when I hit it, that's what I want. All right, so I have to think about the construction. What if I do this? All right, so here, U1, I picked uniformly in the sphere. And then I multiplied it by M. What's the distribution of MU1? Yeah, you have a hint because hopefully the theorem is true. Yeah, why? Can you say that again? I don't think I quite got it.
Well, I remember you had it written over here. We wanted the same distribution for MU1 is equal to U1 is equal to U1M.
Yeah, but we don't have that yet. That's what we're trying to prove. Okay, so we're hoping that that turns out to be true, and that's what I'm trying to check. So first I'm checking it at least works for the first column. Okay, so the first column over here is just uniform in the sphere. Okay, first column over here, I pick something uniform in the sphere, and then I multiply it by this fixed orthogonal matrix. So then that's a question for us, is if I take something uniform in the sphere, and then I multiply by a fixed orthogonal matrix, what happens? What's the distribution of the thing after the fact? You can just guess. We hope it's the same. Yeah, it's the same. Okay, so it's just a linear change of variables, right? I'm applying a map to Rn. The map is a linear isometry, right? Multiplication by m is a linear isometry of Rn. So if you like calculus, you can just write out the change of variables, and you'll see that the distribution is exactly the same. Okay, so maybe that wouldn't be a bad thing to talk about this afternoon in the review session, because we're running short on time right now. But okay, so it's really just calculus. It's a change of variables that says if I make the change of variables y equals mx, and I write down integral formulas for the densities here, you see they're the same. Okay, So this is distributed the same way as this. Okay, that's reassuring. Okay, what about the next one? So the next column is MU2. Okay, so MU2, what does it do? So U2 was picked uniformly in the orthogonal complement of U1, the spherical part. Okay, then we hit it with M. Okay, so what does that do? It moves the orthogonal complement too. Okay, so this, by exactly the same change of variables, this is going to be uniform in the orthogonal complement of MU1. Okay, which means, in other words, the second column is uniform in the orthogonal complement of the first. Good. So that's exactly what's true here. And you keep going. Okay, so it's basically a calculus exercise that this distribution is invariant under multiplication on the left, multiplication on the right. You would think about the rows instead, but like I said, everything is invariant under taking transpositions, so that's fine. So we have constructed Haar measure, and this is my favorite construction because it feels so like, you know, this is what you would do, right? I mean, build me an orthogonal matrix that's as symmetric in distribution as possible. I mean, this is what you would do. Okay, so I like this one. If you're a Riemannian geometer, you laugh at me at this point. Any Riemannian geometers here? Are you laughing at me? Are you laughing at me? Yeah, of course you are. I mean, because this is totally stupid, right? It's totally trivial. I have a Riemannian manifold. Okay, I think I'm not even going to write anything down about this. I have a Riemannian manifold. Okay, I have this metric that on the Riemannian manifold, I can actually use either one of them. So that gives me a volume form. Okay, and the metric is invariant under multiplication, under applying this a linear isometry. Okay, if I use multiplication by m as a linear isometry on Rn, then these metrics are invariant under that. So the volume form that I get by just turning the crank of Riemannian geometry is invariant. So Haar measure in fact, on something like this, it's just the volume form. Okay, so if you're a Riemannian geometer, you can go now. Because we're done. I mean, that's it. It's just the volume form. But I don't like that construction as much. I mean, it makes it obvious that it's really, really natural. But on the other hand, I still feel like it's not something I know how to compute with. Whereas this, I know how to compute with, because this is built up from spheres. Okay, and spheres are things that I feel like, okay, I mean, general, abstract manifolds, I don't know about that. But spheres, I can do that. Okay. Good. So we have a few minutes left, so I can tell you about one more construction. And this is probably the one that everybody else would have told you first, just so you know, so that if you go out in the world and say, I learned how to construct a random orthogonal matrix, if you want to sound, you know, unusual, tell them about this one. But if you want to say to people what they're expecting to hear, you should say this one. So here's another thing that you can do is fill an n by n matrix. Oh, I should give this one a number. So actually, this is number 3, right? Number 2 is Riemannian geometry. So there's another black box for today. 3 is the Gaussian approach. So you fill an n by n matrix with IID standard Gaussians. Okay, so that's sounding a lot more like the approach that you take when you talk about building Wigner matrices or things like that. Wishart matrices, any of those things. We always talk about just like kind of filling in the entries with some prescribed distribution. So, okay, I start and I take a Gaussian random matrix. So it's not the GOE because it's not symmetric. Okay, I really fill in every single entry of the matrix with IID standard Gaussians. So that's fine. This produces a measure which is invariant under left and right multiplication. It's exactly the same argument as the argument for why I erased it, but the change of variables. It's the same thing, right? Because here I have a density which is e to the minus sum xij squared with some constants places, but let's ignore those for the moment. Okay, so this is what my density looks like with respect to the product measure of all of the entries. Okay, so if I multiply by m, I'm rotating space. I'm making a linear isometry of space where y is mx, and you can see that if I look instead at e to the minus sum of m xij squared, okay, this is, because m acts as an isometry, it's equal to e to the minus sum of xij squared. And the change of variables, the Jacobian factor is 1 because it's an isometry. Okay, so it's just calculus again, that this guy is invariant under multiplication on the left by a random, or by a fixed orthogonal matrix. Okay, I can change basis without changing this measure if you like. Okay, so what's the problem? There's a problem. It's not orthogonal, right? So this is not a hard distributed random orthogonal matrix. This is a Gaussian random matrix. It's not, I mean, with probability 1, it's not orthogonal. Okay, so this isn't going to do me any good because I haven't built Haar measure. So I make it orthogonal. Well, what do? If you have a matrix and it's living in R and it's just any old matrix and you want to make it be orthogonal, what do you do to it? You do Gram-Schmidt. Okay, we know what to do. I mean, great, you guys know all the answers. So, I mean, that's what you do, is you do Gram-Schmidt. So this gives me a matrix. So I have a random matrix, let's say G. And then the next thing, so 3 continued, is do Gram-Schmidt to G. Okay? And so then what you have to worry about is when you do Gram-Schmidt to G, have you messed up the invariance under multiplication? And the answer is no. Okay, and if you think about it for a second, think about what you do when you do Gram-Schmidt. So let's say we have our first column, which is x1. Okay, so we normalize it to make it a unit vector. That's clearly okay, right? I mean, we're not going to have any trouble. That's still going to be invariant under multiplication by m. In fact, that's what we already checked. Okay, so what about the next one? You take x2. I can never remember that computer science-y notation with the arrow, but anyway, we replace x2 with x2 minus x1 dot x2 x1, right? With the component in the x1 direction. Okay, I'm not worrying about normalizations because that part I think it's pretty clear that that's going to be okay. So this is what I do. So then if I multiply this, I hit this with m on the left, we would replace mx2 with m of this. So I would get mx2 minus x1, x2, mx1. Okay. On the other hand, if you think about, so this is what happens if you do Gram-Schmidt on the first 2 columns, and then you hit it with m. What if you do m first? Okay, then, okay, so I'm running out of space and time. So if we first multiply by m, then we have mx1, mx2. Okay, and now we do Gram-Schmidt. Okay, then we replace mx2 with mx2 minus mx1, mx2, mx2, and then we're happy because m is an isometry, and so this is equal to x1, x2. Okay, so they're the same formula. Okay, so what that says is that multiplication on the left by the fixed matrix M commutes with performing the Gram-Schmidt process. And so then I'm okay, because I know that I originally created something that was invariant under multiplication by the left, and now because the Gram-Schmidt process commutes with that multiplication, I know that the result is still invariant. Okay? So that's a completely different looking construction. We fill a matrix with IID Gaussians, and then we fix it to make it orthogonal. We do Gram-Schmidt versus this construction where we just build it to be orthogonal from the get-go, but then we have to check and think a little bit more about why it's invariant. Or you can just say, I know Riemannian geometry, you're wasting your time. Okay, so I see that I have 30 seconds left in which I was going to try to answer the following question. Which has to make an appearance. Okay, so somebody should have asked this much sooner, but I'm sure you were all much too polite to do that. I mean, you've been talking about different random matrix models all week, and I'm sure that everybody has talked a lot about what the motivations are and why you should care about all of these different random matrix models. I can't tell you why you should care about these models in 30 seconds. So I'm going to try to convince you over the course of the week. And in particular, so the 4th lecture, on Friday, we'll talk about what I think is a really fun application. So this is not by any means the origin of this area, but you should believe me that since orthogonal matrices encode orthonormal bases of Rn, if I understand what it means to talk about a random orthogonal matrix, it means I understand what it is to talk about a random orthonormal basis. So in particular, that allows me to talk in a very natural way about a random projection or a random subspace. I can talk about a random k-dimensional subspace of Rn. Okay? This gives me a way to do that. And it turns out that there are very interesting properties of Haar measure on the orthogonal group, which turn out to translate into this huge area of randomized algorithms where people do, they build algorithms to do something that's computationally infeasible by projecting whatever it is they're working with, the objects they're working with, onto random subspaces. I mean, this is a huge area that's really important right now in real applications. I mean, people do algorithms doing this, and it has, the whole reason it works is because of stuff that's true about Haar measure on the orthogonal group. So I was going to say a lot more about the motivation, but I think I'll just leave it at that, and I'll tell you a lot more about that on Friday.